Okay, so we're gonna get into conceptual dynamics, the very first chapter, and of course in your course, the title is Introduction, and we're gonna cover the basics, your concepts, your units, and the foundation of dynamics. So think of this as the introduction to how things move and why they move the way they do. Okay? So the very first thing you need to know is dynamics and what is it? Yeah? So dynamics is, well, simply put, it is we study how and why things move. Okay? And we're gonna look at objects in motion, and we're gonna look at the rules, that explain their behavior. Alright, the next thing that you need to think about is, what are we studying? Why should we study dynamics? Well, almost everything moves in this world and beyond, in the universe here. So everything moves. So we want to understand how an object is going to respond if we use a force to it, and how these forces interact between these moving objects. So it's going to help us explain and then predict this motion, okay, in this world. So it's all about motion. Of course, here for this course, conceptual dynamics, we're gonna focus on two types, okay, of objects. The very first one is your particles. So particles they're small and they're very simple, and then your rigid bodies, they're bigger and they're more complex. And of course, we're gonna also take a look at two kinds of analysis. This is analysis. These are objects. So the first analysis is kinematics. So with kinematics, we can look at the motion. Kinetics is another kind of analysis, and here with this analysis, we study the forces that is going to cause the motion. So kinematics, motion. Kinetics, we're going to study the cause of motion. So two objects, particles, rigid bodies. Particles are small, very simple. Your rigid bodies, they're bigger and they're more complex. This one is going to look at the motion, and that one is going to look at the cause of motion. Okay? Alright, now, since we are dealing with two major objects, one is a particle and the other one is a rigid body, so we need to know the difference between particles and rigid bodies. So when you think of a particle, it has mass, okay? And like I said before, particle is very small, so we don't have to worry about its size, and I wrote it here, negligible size. There is mass, but ignore the particle's size. Why? Because it's very, very small. Okay? Your rigid body, on the other hand, it has both mass and size. Okay? Why? Because it's bigger, and complex. So we have to consider how this body, because it has a bigger mass, how it rotates and when it moves. Okay? Small particle, you have mass, but the size is so small that we neglect it. Okay, rigid body, it has mass and is bigger, so therefore it has a a noticeable size. Yeah, and we always think about okay how this rigid body is going to rotate when this rigid body is going to move. Okay, so these are the foundations, the basic concept in dynamics that we break down what we have here in this world and in this universe, as far as we can be able to understand. Okay, and we break it down into, we've got tiny little things and we've got things with a noticeable body. Okay, so that's the first differentiation of objects into two major categories. Yeah, then you've got to worry about the two types of analysis. So the very first thing, kinematics, and I said it's all about motion, because we focus on describing the motion. For example, like the path, something takes, or how long it takes. And here in this analysis, we're not going to worry about the forces causing that motion. Okay, kinetics, of course, on the other hand, we're going to focus on how forces create or how forces change the motion. Okay, so here the definition is, of course, a formula written here, like the kinetics, the study of how forces relate to motion. But simply just try to think like kinetics, we're dealing with the cause of the motion. Kinematics, we're dealing with the motion, purely motion itself. Yeah. So anyway, in science, this is how we study. Okay, we gotta break it down into different methods, analysis, study, and foundational concepts. Okay, got to be clearly categorized and defined, and then we're gonna go into it, more and more details. Okay, so we got the objects, particle, rigid bodies, and then we got how we're going to study these objects by kinematics and by kinetics. First, we're going to focus on motion of these particle, motion of the rigid bodies, and then we're going to look at the cause of these motion. All right. Okay. So then I'm gonna give you an example so you understand what is kinematics and what is kinetics in terms of course, a diagram and terms, that we use in dynamics. So when you look at this problem, your problem is we have a block, and that's your body, because it is a block, so therefore it has mass and it also has a noticeable size. Definitely not a particle. So first, that is what you have to look at it. Am I dealing with a particle? Am I dealing with a rigid body? So in this case, it is a block. Our object is. So make sure every time you read, all right, yes, here in this case is an example problem. Every word that you read, you're gonna think with it. Don't just like read it like block size on a smooth surface. We want to determine its acceleration, blah blah blah. Yeah, you've got to think like, what are you dealing with in this problem? So when you read a block, you're gonna take a look at like, what kind of block am I dealing with? Oh, yeah, it's a rectangular block, and there is a mass. And of course, we're using a symbol m, little m, to describe, the block mass. Yeah, and of course here, look at this. There's an arrow. Yeah, a blue arrow here showing it's going that way. Yeah, and then you have another symbol with unit in it. Yeah, so that's a velocity. Of course, velocity. Okay, and another. Okay, I'm saying unit anyway. So this is actually time. Okay, so velocity multiply. Okay, here there's a multiplier in between these two symbols. So v times, and then your t is your time. Okay, so velocity n time. Okay, so this form of writing, okay, velocity times, and then in a bracket t, yeah, we're actually getting into the calculus, right, part of your mathematics. This is just telling you, yeah, that this symbol represents, yeah, the velocity of the block, because your block is m, as a function, okay, of time. Yes, so every time you look at, I make it, okay, we make it very, very easy for you in conceptual dynamics, is, and like try to make the calculus very easy for you. So every time you see this, we're talking about, we're looking, at this velocity, looking at this block. Yeah, its velocity, yes, as a function of time. Okay, so what does it mean, velocity as a function of time? So it means, so it's just showing you, how this block, right, the speed of this block and the direction of that block change, okay, as time passes. Yeah, you're looking at the velocity, right, against time, like that. Okay, so in kinematics we use vt, okay, to describe the motion, without worrying about the forces causing it. Okay, and that's we're dealing with kinematics. Okay, just purely looking at the motion. So here we use kinematics to describe the motion, and in kinematics we describe the velocity, and another one is right down here, letter a. So a is your acceleration. Yeah, we write it this way. Another calculus, mathematics operation here, which is dv divided by dt. Okay, so this is another mathematics, okay, mathematical formula, I would say, and it's just giving you the formula to get acceleration. Yeah, it means that the acceleration is the rate here. Yeah, the rate. D means change. Yeah, little tiny changes. So the rate of change of your velocity over time. Yeah, we're just looking at how the velocity change over time. So it just telling you, in common, word, how quickly this block speed is increasing or decreasing as time, see the little time, goes on. Okay, velocity, acceleration. Velocity, looking at how the block speed, okay, and direction, because it's a vector, is going to change as time passes. Acceleration, yeah, again, we're looking at how quickly that block, this block m, m block, speed is increasing or decreasing, okay, as time goes by. So anyway, so kinematics looks like this. We are excluding the cause of this motion. We're looking at purely motion. Motion is usually defined by the velocity, okay? Velocity as a function of time, and then it is defined by acceleration, looking at changes in that velocity, okay, over time. Yeah, so we have velocity, acceleration, and we've got time. Yeah, and we have mass, and in this case there is a size for this mass. Yeah. All right, now we're gonna get into kinetics. Yeah, so in kinetics, you see how different they are. So in kinetics, there is a, look at this little F, yeah, symbol, and that is your force, yeah, and force can be calculated. Your mathematical formula is your mass time acceleration, okay. So this little block, yeah, with mass, and we give a name m, yeah, and mass, and you're gonna multiply it with its acceleration, yeah, and you will get the force that caused that motion, so it goes in that direction. Yeah, velocity is showing you where it is going when you use this force to push this block. Okay, it's going that direction with this speed. Okay, and you can understand as you look at this motion over time whether that speed is increasing or decreasing, identified by your acceleration. Okay, it's kinetics, cause of motion, kinematics, the motion. Okay, and the factors, the aspects of motions is described by your accelerations or acceleration and velocity mathematically. Okay, function, and you have this, okay, changes, meaning like derivatives, yeah, is in here. So when we use this formula dv by dt, you know, in mathematic term, we call it, we're differentiating, yeah, differentiating, okay, velocity, how this velocity is increasing or decreasing over time. Yeah, so it's a way to measure how velocity changes with respect to time. In common words, differentiation again is going to help you to figure out how fast this thing in this example or something is speeding up or slowing down, okay, at any moment. I think now you get an idea, yeah, of kinematics and kinetics, and you really have to get this too, okay, for dynamics. You gotta truly understand this two analysis, okay. Kinetics, okay, is to relate the motion to the forces causing it. Yeah, here is your F. We connect the motion, yeah, and the forces behind it is kinetics. Kinematics, we're just describing the motion, yeah, like your velocity, acceleration, and we pay attention how we, okay, look at the speed and the acceleration. Differentiation mathematically, function of time here, yeah. And that's the foundation of your dynamics, okay. Two objects, particles and rigid body. Two analysis, kinematics for motion, kinetics is the cause of motion, okay. I'm repeating this again and again, yeah, for the first a few slides, yeah. All right, let's move on to the next slide. All right, this is just telling you, you know, prerequisite knowledge that we expect you have it. If you don't have it, it's okay. Yeah, try to read, okay, as you study dynamic. So anyway, we definitely okay, want you to be familiar with physics concepts, okay, at least like vectors. FBD is a free body diagram, okay, just abbreviation that we use. General concepts, of course, of motion, meaning basic motion. That's from physics. Yeah, the second one is your static. Yeah, is the other course. You need to know this. Yes, so the equations of equilibrium very important in building things. Yeah, without that, buildings will collapse. Yeah, equations of equilibrium, and of course, we use, of course, this in this mathematicals, okay, equations and many different principles, okay, and disciplines. But anyway, for engineering technology, okay, so you need to know the equations of equilibrium, okay, and that's from your statics part. And again, your FBD is your free body, diagrams. Then mathematics, calculus, but again, you don't have to worry about calculus in this course because we're concentrating on the concepts instead of heavy calculation. But of course, we can separate calculus out of dynamics, even though we try to make it as easy as possible for this major only. So calculus is like is a key, especially to understand the rate of change. And every time we study motion, is nothing about the rate of change, by the way. So your differentiation, your integration, okay, is going to yes, be very important in defining that, okay, rate of change. So physics, statics, and calculus are your prerequisite that we expect that you got it. Okay, if you don't have it, or if you are weak in these areas, then make sure you read more books in, okay, physics, statics, and calculus, please. Okay. And of course, don't worry about too much about it. I'm going to review that for you. What you need, I'm going to review what you need as we go into the course. This is just a cover, for the section cover. We don't need to repeat this. All right, the next section is we're gonna get into units. Basic concepts and units. So let's see what they have here. Okay, so here we have a fun, all right, example to think about. So when you take a look at this example, we have to identify what's missing, from this example defined by this sentence. So the example is my daughter is 6 today and I started her on baby formula. So it's not very complete, completely, so describe a sentence about her daughter, because you have no idea, like how old, is this person's daughter. 6, 6 is a 6 month or 6 years, or what, you have no idea what this number is about. So we gotta use, unit, to identify what the number is about. So here we gotta guess, right? What is this unit, the missing unit is in this example. So since she said, I started her on baby formula, so therefore her daughter age can't be 6 years, because her daughter is a baby, because she's thinking about the baby formula, yeah, to start her, like her baby with a baby formula. So therefore, the unit, okay, for this number 6 got to be months, yeah. So the missing unit is months. So without specifying the unit, it's very, unclear if she's 6 months or 6 years old. And age, of course. So this shows why, units are so important in dynamics. Yeah, even though this is a little fun example for you, and units, they give context to our numbers. Yeah, number is so lonely here, so you need unit of some sort to identify, to put more meaning, into it, to make sure our information is clearly, okay, yes, given to the other individual that you're communicating. Yeah. Of course, in day-to-day life, sometimes we say my daughter is 6. Yeah. Of course, like some people say without the unit, but it would be nice if you use the yes, correct unit or word. Yeah. So it's gonna make more sense to what you're saying. So anyway, so the first example, the missing, yeah, word or unit is months. Yeah, months. Okay, here's another example problem. Um, so the problem is my weight is 55 and I wear a size 8. What's missing? Yeah, from the following sentence. So let's think about what she or he is, okay, trying to say here. So my weight is 55 and I wear a size 8, and we've got to figure out what's missing here. So the missing word is, I would say, okay, you got to come up with the weight unit. Okay, we have pound and then we have kilogram. Yeah. So now we are, like facing to choose to come up with a more sensible unit. Yeah. So we have pound, British, yes, unit, and the other one is kilogram. So if you are only weighing, 55 pound, right, and you wear a size 8, it doesn't make sense, because you will be very light, and yet you will be wearing size 8. Yeah, so it doesn't really fit the first, phrase, and the other is the first, sentence, and the other sentence is contradict to each other. So therefore, out of pound and kilogram, metric unit and the British unit or English unit, we gotta choose the metric kilogram because it makes more sense with the size 8. Yeah. So in this example, the missing word or unit is, and it's got to be kilogram, to make sense with a bigger size, size 8. So what's important is, again, units are very important in dynamics, and you're trying to understand, to use your brain to choose, okay, the correct unit. And I'm going to start you with this a little fun example, so you can train your brain to be able to choose the sensible, correct unit for each example. So units are crucial, units for your clarity and your understanding. Okay. All right. The next example is, I feel very comfortable when it's 28 degrees outside. Okay, here we go. Our number is 28, and we have to, try to decide, and we're dealing with temperature. Yeah, here is a feel very comfortable degrees, right, outside. So for temperature, we have degrees Celsius and we have Fahrenheit. Yeah, so you have Fahrenheit and you have degree Celsius. Yeah, degree Fahrenheit and degree Celsius. So you have to choose either are we dealing with this unit or that unit. And we take a look at our number, and here is feel very comfortable. If you are in 28 degrees, yeah, Fahrenheit, yeah, you're not going to be comfortable, yes, because you will be very cold, yeah. So therefore, this got to be degrees Celsius, yeah, for the unit. Okay, so this is how you put your common sense, yeah, every time you try to solve a problem. In this case, we're dealing with the missing unit problem. I feel very comfortable when we're dealing with temperature, and we have only two, yeah, commonly used temperature unit. Of course, in science lab we use more than this, yeah, but outside Fahrenheit and Celsius. Celsius, smaller numbers, yeah. Fahrenheit we use bigger numbers, yeah. Okay. All right, the next example, the speed limit. Now we're gonna go slowly into the dynamics, okay, problem. So now the speed limit is 100, okay. So every time we think about speed, this sounds like, you know, driving, of course. So we usually use, yeah, if you, let's suppose you're driving your car, we usually say like miles per hour, right? Go 60 miles per hour. On the road, you're gonna see some numbers, right? Road speeds, yes, a sign. So we have like 60, 30, 40, yeah, 70, etc., etc. on the road and highway. So that's miles per hour, because in United States we use English unit, yeah. The rest of the world they use yes, kilometers per hour. In Canada they use kph instead of mph, yeah. So you have kilometers, so that's your k, and then p is per, and then hour is your h. And then we've got miles, yeah. This is American stuff, like, and then per, and then hour. So that's miles per hour in kilometers per hour. If you drive 100 miles per hour, you know, that's usually, you know, above the speed limit, above the most common speed limit that we use. You know, it's very fast, by the way. Even 80 is, you know, that's a highway speed. So it can never be, you know, miles per hour, another common sense that you have to use. So therefore, it's got to be kilometers, you know, per hour for this problem. So the missing word or unit is kilometers per hours, yeah. So now we know why units are important, okay? Because units are important because it needs to make, you know, you gotta you know, make what you're saying, you know, like yes, sense, okay. So because it only makes sense when you have units attached, yeah. Your numbers is not going to tell you, yeah, if you don't use a correct unit. So the number on its own is not going to tell you much if you don't use the correct unit. It only makes sense when it has units, okay, attached. So, and that's because units, they give you meaning, yeah, and context to the number. Number alone is not enough to make sense. So therefore, you've got to use the correct unit, okay, to help other people understand, okay, what you're defining or talking about, okay. So basically, units, they're very important because they make the number useful and also understandable. Yeah. So make sure you pay attention to the units you are using according to the problem you are solving in this course. Okay, all right. So we did like a few examples on units, and we talk about how important they are, to make the numbers useful and understandable. And now we're gonna get into the measurement systems. So you have already taken, I believe, MET 135, and you measure a lot of the objects in the course. So if you remember, we have different systems for measuring units. Okay, so the most common ones are here. I wrote it here: SI system. SI system is your metric system. Yes, and of course the US. What am I saying? Okay, so SI system is what I want to say is like this too. Okay, is kind of like really close. Okay, metric system is the second one. SI system is like we use it in the world. Okay, metric system also widely used in the world, and then of course we have our United States customary system. We say customary because people in the United States, okay, they want to use English system, okay, which is kind of like not a purely English system. It just we call it the U.S. customary system, okay, because we use it in the United States, mainly in the United States instead of the world, So outside SI system and metric system, of course, in U.S. even scientific community, okay, we use these two systems. Outside company heavily depending on the system that they want to do. Okay, so anyway, these are three major measurement systems: SI system, metric, and US customary system. So here is just a table that I give it to you. So this is your units of measure relevant to what we're studying dynamics. So when studying dynamics, we're going to use specific units of measurement. So I put them in the table with column here, the metric US, and of course your symbol here, and then this is going to tell you what it measures. So in metric system, we have meters for distance, kilometer. Sorry, this one is kilograms for mass, and second, of course, for time. In US, of course, a customary system, which is this guy here. We use feet, okay, for distance, slugs, okay, for mass, and of course seconds, for time. So other units, you have Newton, we have pound, and Newton and pound is we measure force with these units. And for energy, okay, we use joules, and we use BTU, okay, BTUs for the energy. And power, we use watt, okay, and we use the horsepower in the United States, okay. So anyways, this is a table for like dynamics unit, and I should say like units used in dynamics, okay. So these units is going to help us describe and calculate our physical quantities that we're dealing with in the problem, okay. So make sure you get yourself familiar with the units that we use in dynamics. Simply we say it like dynamic units. You should get meter, kilogram, second, Newton, joules, and watts, and you should get feet, slug, second, pound, and your BTU is your British thermal unit, and your horsepower. Alright, so this little slide is going to give you information on your units of weight and mass. Yeah, so let's talk about units of weight and mass here. So when you look at it, weight, okay, weight. So here's your equation. Yeah, I boxed it. So with W is your weight. Yeah, is equal to, meaning this is a mathematical formula. So we're looking at what is weight. So weight is, you have your object, and object has a mass, and that mass is, okay, that mass we are studying it with your gravity. Yeah, what is this gravity doing to this little mass? It is doing this force, okay, meaning like the gravity can, all right, pull the mass. And that's what you're seeing when you look at this symbolic equation here. Yeah, so every time the gravity pulls a mass, okay, in its environment, yeah, it's gonna create something, and that's something we call it weight. Yeah, because mass itself without the gravity, it's not gonna be weight. The mass with the gravity, yeah, because the gravity is affecting the mass, and in the environment you're getting a some sort of a force, and we call that, okay, weight. Yeah. So weight is a force because this guy is pulling that guy. So that's therefore we call it force. The word is force, meaning being forced. Okay, because of this, G, which is gravity, because of this, the mass is being pulled. Okay, being pulled towards the source of this gravity. Yeah, so gravity is not letting the mass be alone. It's pulling the mass towards it. Yeah, and that's why we call it force. You're being forced by something to go somewhere. Yeah, so that's exactly what you're seeing here, and you've got to understand this. Yeah, don't try to just memorize W equal to mg, W equal to mg. Don't do that. Yeah, so you gotta know, like, when you have a mass which is being pulled or being affected by a, okay, gravitational force, then we get a weight. Why? Because that mass is going towards the source of that gravity. Okay, and that's what it's talking about. So every time, yeah, every time we got an equation, you gotta thoroughly understand what that is, and you must spend some time. Yeah, I just spent about a minute, yeah, to tell you, like how to understand this little tiny equation, and that information gotta be in your head. So the next time when you look at it, you're not just seeing the symbol, you are understanding the meaning of, what this formula is telling you about. Yeah, you're not seeing the symbol with the letters in it anymore. You're understanding the true meaning of what's going on here. You know, and it's so powerful. The equation is so powerful because we use symbols, which is identified. So this little m means any mass. We have like a gazillions of objects, meaning billions and billions and billions of objects. But we can identify the mass of any of the object by using this little symbol m. We have many different gravity anywhere, like the moon gravity, the Mars, the Mars gravity, the gravity of somewhere we have no idea, the gravity of this planet, our Earth, right? So, but it can be identified by the little symbol G, for any gravity, any weight. There are so many weight. Yes, your weight, my weight, other people weight. The weight of the objects, everything pointing. If we think about the gravity of this planet, our planet, towards the core of this Earth, right? Because it's pulling the originating sources right there. Yes, but it can be identified with a little symbol right there. So how powerful, this formula or mathematical expression is, and how intelligent people were. They come up with symbols, symbolic expression, so powerful. Okay, so weight units. Yeah, these are the units that I am introducing that for you. So this is pound. Okay, the sub is just telling you force. So pound force. You're gonna use this symbol. Newton. Okay, another weight unit. We use a big N. Yeah, N as in Nancy. 0.22481 pound force. Yeah, if you want to change or convert Newton into pound force, you're going to use this factor because 1 Newton is 0.2 pound. Okay? Yeah? Review your conversion from here to there, from there back to here. Yeah? Mass units. We have slug, and slug is 32.2 pound. Okay? And this one is little sub m, yeah, and that is pound mass. Okay, that just giving you the factor for your conversion, and that's of course calculated under your standard conditions. Then we have another unit. Okay, sorry, somebody came into the office and I gotta go answer. So where was I? Okay, so we're talking about the mass units. So we have slug. Okay, so your slug is 32.2 pound mass. Yeah, and we have another one. Okay, this one is just a French word. All right, you don't have to use it if you don't want to. You can just go with a pound mass. Yeah, so pound mass is pound, right? This symbol, and then a little sub m is going to give you the unit, okay, symbol for over 2 pounds. Okay, this is just a French word for pound mass. And then kilogram. Yeah, so we know this, of course. This too is kind of, you don't really use it. Most of the problems that we use in the school is like kilogram, outside also kilogram and pounds. Yeah, we have kilogram 0.06847. Yeah, slugs. So this your conversion factors. You can convert from here to here by using this, either multiply or divide. Yeah, with that factor. Okay. So these are your weight units and mass units. Weight, okay, you gotta know it depends on the gravity. Mass, okay, it doesn't change. Yeah, so mass is C right here. Weight is C with the gravity. Yeah, so make sure you understand what is weight and what is mass. They have different units. Okay. Alright, go on. Then I'm going to show you, yeah, how to identify, yeah, which object has a different weight without doing any calculation, yeah. So if you understand the weight, yeah, conversion factors, right, you should be able to get it without even calculating it. Yes, to guess the weight of each object here. So here is your problem. Your problem is without calculating which one in each of the following sets of objects has a different weight than the others. So you've got 1, 2, 3, 4. Okay, you have 4 objects. Okay, a mug and some sort of, like cup, and then your tea cup, and then the probably tea or coffee cup. Okay, here. And then we have number and numbers and unit. Yeah, so you have 454 gram. Okay, 19 ounces, I think. This is 1 pound, and then this one is 4.4. Okay, Newton. Yeah, this one has liquid in it. Yeah. So when you look at it, okay, you know that there's some liquid in it. It looks like it's empty. Yeah? This guy has liquid in it, and this one definitely have some liquid in it. Okay. So after that, we're gonna go into the given information. Yeah. So it's asking you to choose, one of them here. So when you carefully look at it, it's just telling you, oh hey, 454 gram is equal to 1.001 pound. So meaning this guy, okay, here, and then that guy here are about the same, because it's kind of like a 1-to-1 ratio. There's only like 0.001 difference in it, Then 19 ounces here, this is OZ is ounce, and it's like 1.1875 pound. So you've got like 19 ounces is about 0.1875 over 1 pound. And we've got like here 1 pound, and that's about the same as that. So we're gonna keep this in mind because it's a little different. See, this a little overweight. Then we've got another one, so 4.4 Newton, and you have no idea how the Newton weight is, right? But then it has, like this, okay, information is giving you the equivalent in pound, and that's about 0.989. So if you, think about this, and round it is about 1 pound again, which is about the same as this guy, So you know that this and that are about the same, but this is 0.1875 over 1 pound, So therefore, this is different, okay? And we know that 1 pound is 16 ounces, so 3 ounces over 1 pound, So therefore, okay, we're gonna say like this object has a different weight than the others. Okay, so that's how we solve the problem. You don't even have to calculate it. Okay, we just go by looking at this, because the equivalent, this mathematical, operation, which is this is equal to that and that is equal to this, is very powerful information, that you're getting. So all you have to just carefully, look at it and make sure that your mind is with your eyes. Okay, eye is looking at, and your mind got to be with it or with them, so your brain can interpret what you are looking at. Okay, all right, so another problem is also asking you to go ahead and choose. So you have 4 objects. There are different types of shoes, looks like, given to you, and you have to choose objects on which one of them weighs more. Okay, and of course we gotta think about the earth gravity, which one of them weight more. So let's see the information they give you. So it said 1 kilogram is equal to 2.2 pound, 35 ounces is equal to 2.2 pound, 9.8 Newton is equal to 2.2 pound. So therefore this, okay, they weigh about the same, But this guy, is only 1.4, okay, pound, This is only 1.4 pound. So you know that 1.4 pound, okay, is going to be less than 2.2 pound. So this is 2.2, 2.2, and 2.2, and thus 1.4. So therefore this weight less. Okay? And the question is asking you which of the following objects weighs more. Okay? So therefore this, and then that is going to weigh more. Yes, you got it. This one is 2.2, 2.2, and then this one is 2.2. That one is only 1.4 pound. Okay. Okay, and we do the same thing, and we're gonna choose which objects weigh more. So 227 grams is 0.5, okay, half a pound. And you have half a pound here. 8 ounces is half a pound, yeah? Because 16 ounces is 1 pound. So when you have 8 ounces, that's half a pound. So therefore this and that have the same weight. This guy is only 1.9 Newton, which is 0.49 pounds. So this is your given information. So when you look at 0.43, okay, is less than 0.50. So therefore this weight less, okay? So this weight less, that one weight more, and then more here. Yeah? Okay. I think you get a hold of this. So let's talk about units of length, okay? So these, okay, we have 1, 2, 3, 4 length units, okay? So this two, your feet and then your miles, yeah? They are US, okay, customary system. We don't call English system anymore, so we change British or English system into US system, which is US customary system. We try to get rid of the original name, yeah? And then your meters and kilometers, that's your metric, yeah, system. So the symbol, yeah, feet, FT, miles, MI, and you've got 5,280, okay, feet. Then we have meters, little m. We also have mass as little m, okay, the same. So anyways, the meters for the length units is a 3.28, okay, feet. Kilometers on km, you have 0.6214, okay, miles. Of course, all of this, your conversion, okay, factors, they're very important because the conversions, they're going to help us to compare and work with your measurement, okay, across different systems. So you can convert from one system to the other, yeah? Okay, another example, so we're going to practice guessing, okay, without calculating and play with the units of length. So here we have inches and meter. Yeah, we have numbers, so that's 12 inches, and that's 0.4 meter. And of course, we have information, the equation, yeah, which is 0.4 meter is equal to 15.7 inches. So you're going to compare because we have to compare, okay, the numbers with the same unit, yeah. So therefore, conversions are very, very important. The conversion information equations are very important. So I know that 0.4 meters is actually 15.7 inches. So therefore, when you compare this to meerkats, yeah, so this meerkat's 12 inches is actually shorter, yeah, than 15.7 inches, which is 0.4 meter. Okay, a tall meerkat, this guy, yeah. So this guy is taller, yeah. All right, and the next, all right, is the next problem is gonna again teach you to understand the units of length. All right, so here we're dealing with miles and kilometers, yeah. So this is from Detroit to Chicago, and that's like 238 miles. And we have from Detroit to Traverse City is 331.5 kilometers. Different unit, so we're going to use a conversion. So 331.5 kilometer actually is equivalent to 206 miles. Yeah. So now we have the same unit. So 206 miles, 238 miles. So when you compare, you know that this distance is longer. Yeah. Detroit to Chicago is actually longer. Yeah. So the distance from the Detroit to Chicago is longer is your answer. Yeah. All right. So here is another example, and I put it in a table here, yeah, for you. So what you gotta do is to practice, okay, how to convert the following units from one unit to the other. So we want to go the original unit centimeter, and you want to convert it into inches. Okay, since you've got 5 centimeters, then you've got to find out how many inches is 5 centimeter. Yeah, so in order for you to do that, you need the conversion factor. Yeah, so we know that 1 centimeter, yeah, writing is not very good, but I'll try. Yeah, is equal to, yes, is equal to, you have about like a 0 point, okay, 3. So go back to previous slides, and you can extract all these conversion factors. So the factor is 0.3937, okay, inches. So here we go. So 1 centimeter is 0.3937 inches. So that's your conversion factor. Yeah. So we can now easily convert. So we have 5 centimeter. Yeah. So your first row here in your table is asking us to. My C is very bad. Let me write it. Oh my gosh. Anyway, so 5 centimeter, and then we're going to use this conversion factor to find the equivalent in inches. Yeah, so therefore the factor is 0 point, which is this guy, yeah, 9, and then 7, okay, inches. So that's where we want to go. So where we want to go got to be above the factor line. Yeah, so now you are making a factor, and then 1, of course, 1 centimeter, meaning like this, okay, division is telling you, or a factor is telling you, I have 0.3937 inches in a centimeter. I want to convert centimeter into inch. So whatever that you want to go to, okay, gotta be above, okay, the division line. Yeah, so therefore 0.3937 inches divided by 1 cm, we call it, this is a factor, and you're going to multiply that with 5, okay, because that's your original unit. So cancel, yeah, centimeter. So now you're left with inches. Multiply 5, okay, with 0.3937 and put it in your Excel or calculator. You're going to get about 1.969, okay. And now, of course, you have converted into inches, right? And you do the same thing for the rest of the conversion. Find the conversion factors. That's the first thing you're gonna do. Then you're gonna put where you want to go. So here now I want to go from feet to miles. Yeah, put that, okay, above the division or factor line. Yeah, and then put the rest of them down there and multiply. Yeah, and you will be canceling the same unit, so you will get the unit where you want to go to. Okay, and this is your homework from all the way to here, and you can check your answers. Okay, your answers are here. It's in your interactive, okay, website that I give it to you, your miniature digital miniature textbook, okay, where all the important key points are in there. And of course I'm going to show you how to do it, okay, one conversion, and you do the rest of them, yeah, and practice. So you should be able to convert degree into radian, pound into slugs, kilogram to pound, joules to BTU, horsepower to, okay, kilowatts. Alright, this is another cover for the next section. We are going to get into the basic concepts, yeah, of the units. Alright, so these are the basic concepts we're going to use in dynamics in this course, of course. So we have vectors. Okay, this vector is going to represent, okay, quantities with magnitude and direction. Yeah, space is going to describe when an object, okay, exists. So this is very existential, like the deeper meaning in it. Okay, it's a kind of a problem that we've been solving. Okay, in science. So, anyways, the space is a physical, okay, area um, or distance, okay, and an object occupies or moves through. Okay, so if you know about that much, that's okay. Position is another thing that we need to understand, and talks about the location of an object in the space, okay, and of course at a given time. Time is just activities, okay, activities of the objects in the space, and we measure it, okay. So we're just looking at the objects, um, like where is it in the space, at when an activity happened from now to sometime later, okay. Or we have, of course, time measurements can start at a point and ends at another point. Then you also have to come into understanding of what time is. It's just measurement and how long something or some activity, right, of objects existing in this space, okay, takes to happen. So this is just simply how long something takes to happen. That something is the activity of these objects and the position located in some like position existing in this space that we know. Okay, then we have velocity. Velocity is gonna tell you how fast the objects in the space taking a position, okay, move, and of course in what direction, okay, in what direction is moving, because your vectors is not like scalar, because it's going to tell you the magnitude and direction, and for velocity we're studying how fast these objects in the space moves and going in what direction. Acceleration is we're looking at the rate of this guy velocity when they change. Are they going up or down, or are they going just constantly the same rate? Okay, force is push or pull, and they acts on an object, the object in the space taking the position at a particular time. And of course, so this is push or pull acting on an object, causing, of course, the motion, the motion which messing up, or which is actually the controlling factor of everything that is happening, motion. And then you have your mass, so how much, how much matter an object contains, meaning like we're studying, what is object made of, and how much of this stuff is composing the object. Okay, the stuff in the object is mass. And weight is when that stuff in the object is affected by another force like gravity. We got the weight. So the force this guy exerted on that guy is gonna give you this weight. So the force exerted on the mass is going to give you the weight. And definition is just a force, right? Exerted on a mass by the gravity. Because we know about our planet. We have some knowledge about this planet. Of course, these are all the basic, your foundation, okay, concept in dynamics, and you have to get it. Your vectors, space, position, time, velocity, acceleration, force, mass, and weight. Okay, so try to study and understand the differences, okay, between them. between each concept. So because these concepts are going to help you describe and analyze or what we're studying, motion. Yeah. All right, now we're gonna get into the very first concept is your vector. Your vector, okay? So you gotta know the difference between your scalar and vector. So scalar, it has only magnitude, okay? And what is scalar is like your temperature or mass. And your vector, it has the magnitude and direction, okay? So this, yeah, direction is the difference between the scalar and the vector, yeah. Another thing is the student have the issue understanding what magnitude is, okay? So you need to review, yeah. Of course everybody understand what direction is, where you're going, yeah, with this little arrow showing something is going that way, yeah. So you gotta review what magnitude is. Yeah, so international student need to understand this word. So anyway, so magnitude, okay, is different from direction. Direction, you know that it's going this way and showing with this little arrow. And it's so easy to understand. The direction is showing the angle. That direction is going from this x-axis 0, right? To that much of a degree. That's your angle measurement, and going that way. To that direction, something is going. And magnitude is the size or the amount of that something. Here, something isn't identified. We don't know what that is, but something is moving, and it's moved from here all the way to here into that direction. And this, okay, is the size or the amount, okay, of that movement. Okay, so like you should take magnitude like the size or the amount of something. Yeah. So for example, if you're talking about a speed in this example, so the magnitude is going to tells you how fast you are going. Yes, this from here all the way to here. And if we're thinking about speed in this example, it's going to tell you how fast, and that's your amount. Yeah, you're going. So without considering the direction. Okay. So in a vector, your magnitude, again, here in this diagram we're showing with the arrow, yeah, so therefore from here all the way to here, yeah, is the length of that arrow, and that is your magnitude, okay? And it is representing how strong or how large that quantity is, okay? Right? So the vector has a magnitude, size, amount, okay, how strong, how large, vector, in addition to the magnitude showing you where it's going, yeah, direction. Try to get that magnitude and direction. You will get this pretty easily. You gotta struggle to truly understand what magnitude is, and it depends on the situation, okay, what you're studying or what you're working on. Alright, so now we're going to try to understand scalar and vector by doing this example. Yeah, so this example has two information and is asking you which is a scalar and which is a vector. We know that the scalar has only magnitude. Magnitude is size or amount, and vector, it has the magnitude and direction. Yeah, so here the first problem is I walked 10 miles. It's only talk about, right, how far, yeah, so the scalar, the magnitude in this case is how far, yeah, have you walked, or did you walk, yeah. So I walked 10 miles, and is it a vector or is it a scalar? So you understand, oh, it is telling you, yeah, how far, yeah, have I walked? It is only 10 miles. So that's a scalar because it doesn't, this sentence, all right, this information didn't provide you with direction. Yeah, I walked 10 miles west. And this is going to the west, okay, and that's your direction. Yeah, the word for direction. So you have a direction and you have a magnitude here. You work 10 miles to the west, yeah. So therefore this is vector. Yeah, I work 10 miles and that is scalar, okay. So make sure that you understand 10 miles is only magnitude, the west, okay, going to the west. So if we put that into, yeah, so coordinates is like west, you're going there and you're east, okay, suppose the sun come out here, in this direction. And then, of course, I'm not very good at drawing, whatever. So anyway, okay, this is the sun, so that's the east, okay, and then you have your north, and then your south here. So anyways, you're going that way, okay. So here is the little arrow, and you went, okay. So here is our magnitude. That's about, let's say, 10 miles. Yeah. Then we put the unit MI. Yeah. Drawing is so bad here. Oh my gosh. So whatever. So anyway, so you get the picture of it. Okay. So in your mind, you should get that. Yeah. With the direction vector, without the direction, it's just 10 miles. Yeah. From here to here. From 0 mile to 10, of course, we cut it and we go to the west direction. All right, the next thing is space. Yeah, space is very, very important for you to understand. Anyway, so space is just the region, yeah, where objects exist and then move. Okay, I said everything moves, and they do, yeah. So the objects in the space, they have location in the space, and they exist and they move. Exist means they're just here, yeah. Of course, our human language is only what we know, only human species knows, okay. Yes, of course we try to train the animals and they kind of get it, and some just don't, yeah. So anyway, so we have our own understanding, and that language is limited to only our nervous system. So whatever we're trying to study, yes, belongs to the human species, okay. And of course we try to identify what we have and what we know within our understanding, and one of them is space, yeah. And we know that in our knowledge that all the objects in that space, they move, okay. And that space is just a region, and in there we have bodies, okay. And of course in dynamics we try to study, yeah, study about them and how they're moving. And I've told you so many times about the space, about the positions, about the movement, about the objects in the space, okay. So in dynamics we use the space, we're going to define the position, okay, of the objects in it, and then we're going to study the movements of the objects in the space. And these objects are many in the space, so therefore when you study the movement of the objects, they got to be relative to other objects in the same space, okay. The space can be little, it depends on how you divide it, okay. And you have infinite space. Within the infinite space, we try to study the space that we know around here, yeah, on our planet, and I try to study as much space as our brain can go, yeah, or know. So anyways, the space is just a region. So for international students also need to understand this word, what region, okay, what space is. Again, not just a word, but try to understand it from the engineering or science, yeah, point of view, okay. Of course, in dynamics, yeah, we we use this definition is because we want to make sure that the space that we'll try to narrow the scope of the space, okay. The space is infinite, it can be big, it can be small, but here in dynamics, if you carefully read it, see under considerations, what it meant is this word region, okay, is just a part of the space, okay. So like a room, a field, even the space around, around the bodies or object, yeah. So in dynamics, this region, helps you to focus on the specific area, where motion of the forces that we are studying are happening. Okay, so anyway, so to make it simple, we are we are studying in a particular defined region, and we call that space. We're narrowing down, to solve the problem that we try to study instead of the real, infinite space, okay, that we're in, So that's let's say, like, as far as the universe can go, and here is in the world, and of course this is not scaled, and this is a region, okay. That's infinite as much as we can imagine, or our knowledge can think. Space, it's like a little region in the real space, and we also call that a space, for us to study the dynamics. Okay, since we narrow the space that we are studying, and we call that a region, and in dynamics we study the objects in that region systematically. And so in order for us to study the objects in a region systematically, we have to define that space, okay. To define the space mathematically, okay, we use something like this, okay. This cross that line and that cross this line, so you have like a three distant lines, okay, crossing at this point, and we call this a coordinate system, defining your 3D space around it, okay. So Cartesian polar coordinate systems, we have different coordinate system. This is just showing you a coordinate system. So this is how we define the region, define the space, okay, for us to study objects in that space, okay, in dynamics. So we have x-axis, y-axis, and z-axis. They all cross at this point, and we call the cross point origin, okay, because this is where you are going to study or measure, okay, distances. So this is your reference point, starting point, beginning point, okay, and you will measure the distances, from that point in these direction, so you have 1, 2, 3, 4, 5, and 6 distant direction along the coordinate axis. Of course, you have 360-degree direction all around each axis, okay. So if you think about the direction, that's a lot though, you can point to many different so in your brain in 3D, sphere is going to define all the points that your arrow can go, so I can put infinite arrow right at all of the points. So even though we draw it on 2D, you have to imagine it like a three-dimensional sphere or ball, okay, around these axes, and the surface contains billions of points, and each point, okay, you can end the arrow at it, okay. So you have so many directional arrow coming up from this origin. If you combine all the arrows with every single point on that sphere, you're gonna get a solid spherical body. Yes. So anyway, so if you just want to point and study a single little tiny, all right, a particle at that point, see, that point is from here to here magnitude, that distance far away from the origin and end on the surface of that defined, right, spherical spherical object here, and we're concentrating only on this little particle right there, okay. So we know that the direction of that particle is this distance away, this magnitude away from the origin, pointing to that direction. Okay, so that direction can be measured from any axis, that much of angle from each axis. Okay, so anyway, so when you look at it, you see like, that's just three axes. I know it, but when you go into a deeper knowledge, a lot going on in there. Okay, so anyway, so that's the space, defined space. We're going to use a coordinate system. We call it system because we want to study a body, okay, systematically. And of course we have different coordinate system, Cartesian, polar, etc., etc., and I will tell you one by one. So Cartesian is like you use this XYZ axis in a 3D space. Your polar, when we say polar, we're talking about these angles. See the angles from this axis. So angles and distances, okay, for circular or rotational motion or whatever body or particle that you are studying, okay. So this coordinate system is going to help us describe the position, again, position of the object in that space, so the object position is located by using these three, okay, axes. Then you got to know another, right, foundational concept or basic concept in dynamics is position. You kind of get an idea of what position is. In this space, the object is located, at a particular position in the defined, right, space. So the position identifies where a body that you're interested in, to study. So where a body is located in space, okay. So right now this space is not the space outside. This space is not a narrowed scope, okay, narrowed down or scoped down space that we are studying within that coordinate systems now. So the position defines where a body is located in space from the point of dynamics, okay. So position is going to tell you exactly where an object is located in space, and it's like giving you address, okay, an address for the object within that specific region. Again, that specific region is coordinate system. So the address is composed of XYZ distances, okay, measure from that origin, point of origin where all of the axes cross, okay. So your address is going to be measured, okay. Oh my gosh, okay. Let me erase that. Measure, okay, from this cross point, all these, direction that I just explained it to you with the spherical body around it. So if you're here, so this is a body, you're gonna measure from here to here. You can measure, see that you have distance and you have direction, location, space, where body is located in that space, measured by the axis defining, that space around that body of interest, okay. So now we have studied what position is in dynamics. So the you need to know, okay, since we have studied the position, you need to know the units of position. So we will go back to our length, your metric system, your meters, and then your kilometers, your millimeters. So this belongs to the metric system, and then your US system, which is your feet in inches, and then your miles, right? So these are all your US customary system, and I just call it US system. And of course, a US customary system is a new name for British or English system. It's the same system, it just change it to change it to United States, okay? New name, yeah. So anyway, so these are the units of position, and they are based on, again, on the length, okay? Because we're dealing with the coordinate, yeah, system, and you're studying the object in that coordinate system, yeah, which we call it defined space. And every time an object takes, yeah, a place in that space, we call that the location that that object is, okay, staying, okay. So you got the position and you got the address defined by the coordinate system, and they depend on that measurement, okay, coordinate system. So I believe that you get it, okay. It's very important. The very first introduction chapter 1 is very important for you to understand dynamics, okay. Your units, your basic concepts, you gotta get it, the meaning of it, not reproducing the memorized definition. You truly have to get the deeper meaning of each of it, okay. So that's your homework to study. So these units is going to help us, yeah, describe how far and where the object that we want to study is located in that system, yeah, defined by the coordinates. All right, the next one is the next concept, the next basic concept is time, yeah. So why do we need time in dynamics? So that's because most of the variables, yeah, most of the things that describe motion, variables are just the things that describe motion, like the one that we just studied, position, yeah, velocity, acceleration, yeah, they change. Everything change in the environment. Yeah, they do one activity at one point, and later on they do another activity. Yeah, so the objects in the space, they're doing something. At this point they're like this, the next one they're taking another position or something, and that, all right, change is called yeah uh, change over time, yeah, because it's one activity now, one activity then, and one activity is going to be in the future, yeah. So when you look at that, there are different activities, all right, in different position in that space. We're looking at these, you know, describing that motion, or we're studying the change of them over time, yeah. So and time is, if I just it's just a measure, yeah, measurement. So let's say like I'm studying, let's say two, two things here, and they're like that, okay, at this point, and then later on you come back and see, and they're like this, okay, move around another point. So see, this is the first point, and that's the second point, yeah, and that's the third point. So from here to here, that activity is different from this activity because object 1 is here, object 2 is there. Later on, object 1 is here and object 2 is over there, yeah. So activity 1, activity 2, they're different, and that is called the change, and we use a little, triangle sign for the change of the objects that we're studying in the space. See that? There's a change. So when you measure the time, okay, from here all the way to here, let's say that's a 2 second, okay, 2 seconds. So 2 seconds, this two little tiny objects change, okay, change with motion that way, okay. Now they have different position in that space. Yeah, position 1, position 2 different. Position 1 and position 2 of the second object different. and we're looking at it over time. Yeah, and this one, let's start to use the symbol T. Yeah, you're looking at that activity over time from this point to that point. So from here to here, okay, and we call it that time is 2 seconds. Whatever that caused that two little particles to stay apart that much is caused by some force. Okay, because of that force, they move, and they move that much apart from each other, and that happened in about 2 seconds. Okay, so this is what we call studying, right, about the motion of these particles over time. Yeah, so time is going to help us understand how motion change or evolves, and time is going to allow us, okay, to calculate these changes. Calculate meaning, how much is the change from here to here? The distance was that. From here to here, the distance is now a new distance, longer. Yeah, that's shorter. So the change is, this much. Okay. So like that. Of course, the direction was like this, going that way. Now the direction tilted to this way. See that? So these are all the changes that we're studying. Okay, even though in a very simple problem, we can see changes in there. Over 2 seconds of time. So anyway, that is time. Yeah. If you put it in a formal definition, it's like variables that describe an object's motion, or function of time. Function means we're just looking at these activities over time. Position, velocity. So when it moves, it's gotta move with a speed. Yeah. Do they move gracefully, or do they bounce up and down? Yeah. So acceleration and speed, slowing down, or going up or down of that velocity. You're looking at that acceleration, velocity. They are having a speed to go from here to there. Yeah. So when they do that, the position they change. Okay, the original position change. So anyway, so that's your time. Okay, now we know a little bit about time, the activities from one point to the next. Okay, and now we gotta know the units of time. Yeah, units of time. So time is a measurement. So everything that we can measure, we have units. Yeah, and we use seconds in our system. Yeah, in our U.S. customary system. And of course, we have minutes. When you have about 60 seconds, you've got 1 minute, and 60 minutes of those, you're going to get 1 hour. Yeah. So the units of times, they're pretty standard across the systems. Yeah. So the basic units, second, minutes, your hours. Yeah. For these are larger intervals. Yeah. Again, a point is a measurement from time is a measurement from one point to another. And when you study from point to point, you get, my drawing is very bad. Anyway, you got an idea. Here's a point, second point, and the third point. When you study, activities from point to point, from point to point, you got a timeline and the activity that's going on that timeline. Yeah, and this point to that point is one interval. From this point to that point, another interval. From this point to this point, another longer interval. Yeah, so these are the intervals. We call it time interval. Yeah, so these units, second, minute, hour, is going to help us measure. Measure and compare the duration that happened in that interval. Yeah, so you know that the time is a measurement, and we measure by using points, and we are measuring the activities, okay, of the objects, because that's all we have anyway in the existence. Yeah, so objects and whatever they're moving, however they're moving from one point to another. Yeah, so let's say January and February, what is this thing doing? From February to March, what is this thing doing? 1 second, 2 seconds, 3 seconds, an hour, 2 hours later, 3 hours later. Yeah, a year, the second year, the third year, Yes, so there are many different kinds of unit, okay, in time, but the method is the same. You have point, you connect the first point to the second point, you got the first interval. You connect the second point to the third point. In your study, you got the next interval. The beginning of the point and the ending of the point will give you a bigger, even larger interval. And we call that the time line, measurement line. We're looking at the activities, okay, of whatever you have interest in. From this point to that point, what is it doing? From that point to this point, what is it doing? From this point to this point, how did it happen? Yeah, well, the change, how did that happen? Okay, so that's what we're doing by using this time measurement. The next basic concept is a velocity. Yeah. Well, a velocity, you gotta know what is velocity, and you gotta know is that a vector or a scalar. So velocity is gonna tell us, yeah, how fast a body is moving. Yeah, we're in dynamics, so all about motion. How fast a body is moving, and that's your velocity. We call it speed. Yeah, and of course, because this is velocity, we also want to know the head of this arrow is, telling us where it's going. Yeah, direction. So you have a body going in with in a motion, the body in a motion going somewhere in a particular direction. Yeah, because since it has a magnitude and direction, it is a scale. It is a vector. Okay, so this makes the velocity a vector. How fast the body is moving and in what direction. Yeah, because it includes the, again, magnitude, the speed, and the direction where it is going. And essentially, yeah, in other words, we call it the rate of change, okay, of position. Yeah, so now I'm going to draw it. Every time we think about time, we have 2 points because we're studying from this point to that point the activity of that body, okay, in this interval, and we call this a little time interval. Yeah, and in that interval, this guy changed from this point, okay, to that point. And the point, of course, all right, since we're studying in a coordinate system, and that is the location, which is the position in that space. Okay, so from this position 1, yeah, position 1, the body has moved to position 2. All right, so position 1, I'm moving to position 2, to that direction. Okay, we have magnitude is from here to here, direction going that way, velocity is the speed, it is a vector, it is the rate of change of position, okay, over time. Now I'm going to put position as a S, okay, because that's how we identify position mathematically, yeah, instead of a common word position as P. Yeah, so you have position, you have time, and you have velocity. Yeah, so velocity is just the rate of change. Okay, so this little d means just a calculus symbol telling you the position has changed, okay, over time. Right, this d is telling you change. What is changing? Position is changing, yeah, from this point to that point, and that change happened in that time. Okay, time also changed from this point to that point. Okay, position from this point, and you have two lines. One is a position line and a time measurement line. Yeah, position also measurement. So from this point to that point, location measurement. Time is a point, okay, measurement, or how long does it take for that position change to happen. Yeah, change in position, change in time, and we studied that 2 different changes, and we call that velocity. Okay. Don't think that there's only one change. No, there's two different changes, because this delta mean the position has changed. It has changed, okay, in that interval, yeah, interval time. All right. All right, the next one is speed. Okay, this is just a section subtitle, yeah. And under velocity, we study velocity, and then we're going to study speed. Okay, so if you take away the direction out of the velocity factor, we're going to get only the magnitude, and we call that speed. Okay, so speed is simply the magnitude of the velocity. So if you want to know the speed, you've got the velocity, and we're not gonna think about or consider the direction, and you're gonna left with only magnitude, and we're gonna call it, okay, little v like that, and that is going to be your speed. Okay, just magnitude, purely magnitude is going to be your scalar, yeah, and we call that speed. Speed is the velocity without the direction, yeah. Speed is a scalar, not a vector. Why? Because it doesn't include direction. Okay? Alright, you got it. Now we get velocity, what that is. Along with velocity, we study speed, yeah, without the direction, velocity with the direction. And now we need to know units. So the units of velocity, units of speed, they're gonna measure how far, you know, something moves over time. Yes, don't forget the position, don't forget the time change, position change, and these units here, you know, they're typically expressed, okay, as length per time. Yeah, now we're bringing in the point to point, yeah, interval study, which is your time. So we're studying the length, yeah, from one point to another. Don't forget to change, okay, that and that, okay, is the two different variables. So your position is changing from here to here, and you're looking at from this point of time to the next point of time, okay, because this is your timeline, and that's the length line, okay, the distance line. People usually draw, because they're lazy, so only one line, and put two variables on it. If you draw two lines, you understand that's a distance line, and we're looking at the particle change of distance from here to here on the timeline. Okay, all right. So the movement is your event, yeah, or activity. Okay, so these units are typically express your length per time, yeah. Per is this, see this little slash, okay, line here, so that's your division, okay, length divided by time, so length per time, so such as meters per second, yeah, meters per second. So you can write it this way, yeah. Traditionally the line is horizontal, yeah, but if we write it in abbreviation with this slanted line like that, so unit, yeah, meter per second is just a division, so factor, yeah, meter per second, of course you have some value here, and kilometer per hour, this one is feet per second, okay, miles per hour, so you have meter per second, kilometer if we write it formally, yeah, per is this line, and then hour, yeah, and then you've got your feet, so that's your US customary system, and that is going to be feet divided by second. When you call it, we call it feet per second, per PR, yeah. And of course miles, your car, yeah, distance measurement is your mile per, and then hour. Okay, so anyways, these are the units of velocity and units of speed, yeah. All right, Then the next concept is acceleration. Yeah. So if you get velocity, you got acceleration. It's because acceleration, okay, we just study, yeah, velocity, the changes of velocity from one point of time to another point. Okay, so acceleration is nothing but we're looking at the change of the velocity. Yeah, changes again, right? We write little d, that means a small change, okay, of velocity over the change, okay, of time. Two changes, all right, don't forget that. um, from here to here, yeah. So your body is moving like that. This is your timeline, and of course we're watching the activity, yeah. And the body is taking from one position to another, and it get, okay, it gets a speed, okay, and that speed is going to change over time, whether first it goes with, higher speed, then it goes reduced, right, with a lower speed. So now you have two changes, yeah, velocity. So when you draw acceleration, you should have three lines. Okay, so even though we draw one line, you actually have three lines going on. One is a time measurement line, another one is a position line, because the position changes, yeah, that's why you get the velocity. And the third line is a velocity change, because velocity going up, going down, see. So you have a three distinct line, got to be in your head, yeah, even though you represent with just a single line formally, yeah. So acceleration, change of the velocity over that same time. Your velocity is a change of the position, yeah. See how easy now, yeah, to write it down. So the change of the position over the same time right there, yeah. Of course that time is from point to point. So in this example, I make it easier to go with from first point to second. It can be many intervals in there, and your position is not only one change, but it can be multiple changes, yeah. So you could go up and down, constant, yeah, velocity, go down again, go up again, or yeah, like that. So anyway, so the change of velocity over time, the change of time is your acceleration. Okay, since you're dealing with another, okay, change, which is velocity is defined by this guy, yeah, defined by this guy, yeah. You have another time factor in there. See that? So the change of location, which is your position, is your velocity. So this guy is actually this guy, yeah. So therefore, yes, if I have to put this, of course, you just plug it in, yeah, into here, right there. So if you plug it into here, you're going to end up getting times square, yeah, because this will come down to here, yes. Okay, so you will get like that. All right, so this is what you're going to get. Okay, yes, all you have to just put this into this, and you're gonna get this, because this is that, yeah. So you're gonna get look at this, I forgot the t. I gotta write I forgot this t right there, yeah. So we have t here, and then we have like that. Okay, so this 2, we write it abbreviatedly because that is position line, which is, we just said it, position is the length, yeah. So L, length, and you've got 2 times here, yeah, TT, and that's your time square. So meters is the length unit, per second is your time unit, It is a square because you have 2 times here, so meter per second square. Yeah, so your acceleration unit is length divided by second, in this case square. Yeah, another one, US customary system feet, okay, divided by time square, which is second square for this unit. Okay, all right, so this got to be in your brain. Yeah, every time you read this. Yes, so when you see length per time, you know that we're looking at the bodies. The body, they change position, yeah, from this point of time to there, with first going that way, okay, speed up, and then later speed down. So that's a change of velocity. Okay, all right. The next basic concept is force. Of course, we need to know, is it a vector or a scalar? Yeah. Force, I have already explained a little bit about it. Is that's a push or pull. Yeah, that acts on an object. Okay, we're studying anyway particle or object. So there's your object. It can be a particle or a body, and then you go into yes, push. Yeah, or are you pulling? Yeah, are you pulling it? Okay, so push or pull that acts on an object. Okay, of course, if you have an object, you always have a mass. Okay, yeah, so an object with a mass, meaning the stuff that made of that the stuff that make that object is mass. Okay, so something is pushing, and we call that force. Yeah, something is pulling that object, and we call that force. Every object has the same mass. Yeah, so every time you push or pull, it's gonna generate acceleration because of the position change. When the position change, you have the velocity, and everything is happening from one point of time to another in that interval. So therefore, you've got acceleration. Yes, so the force can change the velocity of an object if that body was initially moving. Yeah, not everybody is like at a rest position. Okay, they could be in motion, but you push it. So if an object is going with a velocity and you push it, you automatically get the change of velocity. Yeah, going with one velocity and get another velocity. When you push it, after the push, you're gonna get the acceleration. Yeah, so force can change the velocity of an object by altering its magnitude, yeah, direction, or both. Yeah, it might be going that way at first because you push it down, and it's gonna go maybe that way. Yeah, you pull and it was in one direction, and you might pull it this way or that way, right? Even though you try to pull horizontally, sometimes it comes downwards or upwards like that. Yeah, depends on how you balance. Yeah, how the original, yes, force originator balances itself. So the force can change the velocity. You're going with v1. After the pull, the same object is going to get different velocity, and there you generated acceleration. Okay, so you've got the change in magnitude, the change in direction, and both or both. Okay, magnitude meaning the distance, yeah, the distance, the length, because your acceleration is based on velocity. Velocity is based on the position. Position is the distance. Yeah, when the position move, you got a distance, which is measured by the length. Yeah. So force, when you think about the force, it comes with a vector, because it has the direction, it has a distinct direction, So because it has both the magnitude, the distance, how far it moves, and the direction, where is it moving, where is it going. So the magnitude is the strength of that force, and because of that strength of that force, this object is going to take a different direction and a certain amount of distance, or so the way the force is applied is going to change the original direction of that object. The strength of the force, the way the force is applied. So it has magnitude and it has direction. So force is a vector, Acceleration is also a vector because it has, it describes a change in the velocity, which is a vector. That means that it includes the magnitude and the direction. So the magnitude of acceleration is the amount of increase or decrease of the velocity. Direction is because of that change in position. Where is it going? Okay, so now we're gonna go into units of force because we know something about force. What is force? So we gotta go back to your physics. Okay, so force, the unit of force, we usually use the Newton's second law of motion mathematical formula, and that's from physics, which is your force is equal to object mass, okay, times acceleration, okay. So force equal mass multiplied by acceleration. So this is in SI system, you want to have the unit of force, and we call this, okay, Newton, and that's the kilogram meter per second square. Since you're dealing with acceleration, that is meter per second square, 2 times, and then your location, which is your meter distance, and then your mass is in kilograms. So therefore you have kilogram meter per second square. We call it Newton because this guy found out about it. So Newton, to honor him, we gave capital N, Newton, for kilogram mass acceleration meter per second square. So when you look at it, you know that's force because this is going to give you mass, and that is going to give you acceleration. Every time you see mass and acceleration, you got a force. Okay, so another one is your US customary system is pound, okay, which is slug feet per second square. That is acceleration, feet per second square, acceleration unit, and that is the mass unit, slug, right? And that is your US customary system, and we call it pound. So 1 pound is equal to 1 slug feet per second square. So these units is going to reflect how your force is proportional, to mass and acceleration. So if we change it into proportionality, your forces are directly proportional to acceleration, meaning when your acceleration increases, your force is bigger. Acceleration decreases, your force is smaller. We can assume we're assuming mass is constant in this proportion, and of course you can make, if your acceleration is constant, you will have your force directly proportional to your mass. If you have a bigger mass, you need bigger force. If you have a smaller mass, you need a little force. Okay? Alright, then after force, you've got to know mass and weight. Yeah? So your mass and weight, they are related, but they have different concepts. Okay, so okay, one moment. So when you think about mass, yeah, we're thinking about the stuff in an object. Yeah, so when you look at the elephant is composed of elephant material, which is COH, okay, and life material, we call it, is about chemical materials. Okay, so that's a quantity of matter in an object. It's called mass. Yeah, of course you don't want to go deeper. What is mass? Mass is the material of any object, and in this case we have an elephant. Elephant is a biochemical material because it contains carbon, hydrogen, and oxygen. So if you go all the way down to the physics, right, level, we have level of life. This is an organism, meaning organs are the parts of this system, elephant system. Yeah. So if you go all the way down to the very smallest particle of that mass, you're gonna go all the way down to the quantum level. Yeah. The smaller we go, it's the same thing. It doesn't matter animal, plant, or us. Yeah. Or the lifeless objects. So if you go all the way to the smallest level of matter, yeah, and we are the same. Okay, but when you go up, yes, in a system level, we're different. Yeah, because of the features on the object. So anyway, so the quantity of matter in an object is your mass. Now it is a measure, yeah, of an object resisting to acceleration, and we call that inertia. So mass is just a measurement. Why? Is because you have matter, yeah, in an object, the object of your interest, in this case elephant. So when you measure the object's resistance to the acceleration, meaning like the stuff, right, of that object, even though you try to push it or pull it, yeah, that object, okay, it's not going to go, okay, meaning like it's not going to gain acceleration. Yeah. And we call that resistance. All right, resistance, because mass has the ability to resist to the change. Right, change of motion. When we say acceleration, we're talking about the change of the position, the change of the velocity, the change in the motion, and we call that inertia. Okay, even though you apply a force to the object. So mass is a measure of an object's resisting to acceleration, meaning it's inertia. And unit, we use it, all right, kilogram in SI system, and we use the US system is slug. Yeah. Mass, again, without the direction, just the magnitude, so therefore it is a scalar. Yeah. And when you think about weight, yeah, that's the force exerted on that object because of the gravity, right, pulling it towards the source of that gravity. So here, we have a gravitational force on this elephant, yeah, and that's going to be your weight. Yeah, so the force exerted on an object because of the gravity. You can calculate again already, yeah, I have already explained this. Weight is your mass affected by gravity. Weight, your mass, and this is gravitational force, yeah, which is your acceleration, yeah, due to gravity, even though we loosely call this one as a gravity force, yeah, gravity force, but this is actually okay, since this belongs to the planet Earth, we call this acceleration due to gravity. Okay, gravity is the force, so that force generated acceleration on this object, and we call that, okay, acceleration due to gravity. Of course, in the beginning, yeah, we try to teach you, yeah, when you start to learn the dynamic, we try to teach you, oh, there's a pull by the gravity, even though we write it with the, like the same symbol. Later on, yeah, if you continue to study, yeah, from the basic concept, then we start to write like this for the gravity, which is your force, yeah. And because of this, on that, you're gonna change the acceleration of that object and become a little g like that, yeah. So you have weight equal to mass times acceleration due to gravity, same as your force equal to mass times acceleration, yeah. So now your force is called weight because we are looking at the mass of object affected by a force, which is gravity g, and generated acceleration g. You multiply that and you're going to get your weight, okay? This is your mass, acceleration due to gravity, and then you're going to get your weight, okay? I spent a lot of time telling you repeatedly, okay? So you should get what is mass, what is weight, quantity of matter, yeah? That's a force. This force happened because of the gravity force exerted on the object, okay? And it has changed the generated the acceleration, meaning change of velocity happened on that object, okay? Mass is just a measure how much that body resists the acceleration that can happen because of force pulling or pushing it, yeah, on that mass. And this mass actually resists this, yeah. If it cannot resist, it's going to generate that force, okay, or it's going to go with that force, yeah. That's what it's talking about. So weight is actually usually in balance, yeah, because this guy is resisting the pull by this force, yeah. Even though we identify that with a change in acceleration right there, this is resisting that. So you can stand up, yeah, on the earth. Let's say we're on the earth like the people are, yeah. So you don't collapse or just go flat on the ground, yeah, towards the gravity. If you don't have the resistant force, yeah, we're all you're gonna be you cannot be able to take a posture, yeah, on the surface of the planet. Yeah, you will just go fall onto the surface of the ground like that. Yeah. So anyway, so you need strength, energy, resistance, and the mass is going to give you that resistance. We call that inertia. Yeah. So if I bring the location, which is your S, okay, position, when you think about the mass, it just a matter, so intrinsic property of that object, and it doesn't change with location. Okay, mass never change. It doesn't change. Maybe location changes, but it doesn't change with it. But the weight, this guy, yeah, depends on your gravitational field, and that's going to changes with your location or position. Okay, so it depends on the location, your weight changes. Yeah, so weight is less on the moon than on the earth because the location changes. The moon, the location of the moon is different from the location, okay, of the world, and you on the earth, that location is different from you on the moon, yeah. So therefore the gravitational field is different. Changes in the location is going to give you changes in the weight, yeah. So basically you weigh less on the moon because of the different, yeah, gravity that we have on the moon and on the earth, yeah. This is just trying to give you, yeah, yes, a problem, and I want you to think, yeah, what could make you weigh less? Yeah, what can you do to make you weigh less? So if you go on a diet and you're gonna lose the mass, yeah, so we know that weight depends on the mass and the acceleration due to your gravity force. Okay, so this is directly proportional to mass if g is constant. Yeah, so therefore the weight is larger if your mass is larger. If you lose the mass, of course you're gonna weigh less. Yeah, so if you go to the moon where your acceleration due to gravity is less because the gravity on the moon is smaller than the gravity, all right, on the earth. So if you go to the moon where g is less, yeah, the gravity on the moon is about, I think, 1/6 of the earth's gravity, so your weight, yeah, it's gonna definitely make you weigh less. If you go on a higher elevation, then you have a little g, yeah, because of the distance, yeah, meaning like it's more far away from the original, yeah, far away from the origin of the gravitational force. So therefore, your g is less at higher elevation. So therefore, yeah, at higher altitude, your gravitational force decreases slightly, yeah, because of the increased distance right here from the Earth center. So it's gonna have you're gonna have your reduced weight. Yeah, it means that could make you weigh less. Yeah. So go over that and really think about it, so you get you understand, okay, how weight is directly proportional to acceleration due to gravity. Yeah, so even though you have mass and acceleration due to gravity, never ever forget there is a causing force, which is gravity, which is g, big G. Okay, all right, some textbook use the same little g. Okay, so you have like a acceleration due to gravity is g, and you have gravity little g, so it's confusing. But of course, traditionally we use a symbol big G for gravity. Sorry about that. I was fixing this in the office. But anyway, let's continue. So the next thing that we need to know is is weight a vector or a scalar? Yeah. So we're gonna think about that again. So when you think about the weight is your mass and your acceleration due to gravity, yeah, and weight is the force. It is a force due to that gravity, okay, acting on a body. Even though this is acceleration, we loosely call it a gravity acting on the body, yeah, when you initially study the weight like that. So yeah, gravity has, again, yeah, a big G. It has a magnitude and direction because it is a force, yeah, and that is, when you think about it, usually pulling towards the center, yeah, center of, let's say this is Earth, so it's going to be pulling like that. Your G is right here, yeah, like that. Okay, like towards the center of the Earth. Suppose this is the Earth. I'm gonna just write the E here and making that weight, okay, a vector. Why? Because look at this, you know, so if your object is right here, is pointing towards the center. Yeah, so every arrow head is defining the direction. Yeah, that this magnitude is going. So therefore, from here to here is the magnitude of the weight. Your mass is here, let's say, okay, being pulled by that gravity, and you generated g, which is acceleration due to gravity. So when you multiply your mass and acceleration due to gravity, you got weight. Okay. Mass. So when you think about mass, it's just a measure of the amount. Okay, if you think about that object there. So when you carefully look at the object is made of something, material. Yeah. So that measure of the amount of matter in that body is your mass. It has only magnitude. It doesn't have direction. We don't think about this. Okay, just pure mass right there. So therefore mass is a scalar. Okay. All right. Then we have mass. And we're going to go into units of mass. So we have kilograms, yeah. The SI unit for mass, yeah, right here. And then of course your slug. Here is the cartoon for you. At last, a unit with a beautiful name, slug. Yeah, tiny little creatures right there. Anyway, so the unit of mass, that's a US system, slug. And then your weight is Newton, of course. I already told you, pound, yeah. So that's your SI, and then this one is your US, your SI, and then your US. Mass is kilogram, slug, weight is Newton, and pound. So weight is derived from the mass using the formula already. Yeah, you should get it by now, which is mass time acceleration due to the gravity. Okay, all right. And this is your weight formula. Yeah, this is just the force behind the acceleration. Okay. All right. The next thing is a scientific proof. Yeah, and we say that particle, they're very, very, very small. It's really difficult for us to define its size, so we neglect it. But it does have mass, yeah? So they have mass. And how do we prove it? Is this scientist, Peter Higgs, from University of Edinburgh, yeah? In 1966, he proved it. Yeah, so why particles have mass is because of his experiment, yeah, and the theory that proved that particle got mass is called the Higgs field theory. Yeah, so it is proposed by this guy Peter Higgs, and Higgs field is a universal field. Yeah, and what happened in there in his experiment is particles moving through that field. Okay, they experience disturbance, yeah, because of the Higgs particles. And every time you have a disturbance, right, a resistance, we said the mass resists the acceleration. If something is resisting, then that something has the mass. Okay, so the Higgs field is described as a kind of cosmic molasses. Okay, molasses is kind of like liquid, right? Sticky. So anyway, so filling all the space. Okay, so you have like a Higgs field. I can draw it with a little thing like that or line. Yeah. So anyways, just make it easier. So just draw a line like that, and we're gonna pretend that's a Higgs field. Yeah. And so it is filling, let's say, this space, you know, in the experiment. So when the particle moves, okay, through that field, okay, what they do, how they behave, they wade, yeah, they wade through And this is the experiment, right, testing Higgs particle. I'm going to say the line is the Higgs particle. Of course, these are all particles. So when the field, yeah, here identified by the line here, so Higgs particles are the line H, and the particles being tested, okay, is going to interact with the Higgs field. And Higgs particles and the particles I'm just going to call it P, yeah? So when the P collide with H, okay, they weight, meaning they weight the particles clean to, Higgs particle clean to that particle. So let's say if you have, I'm going to make it bigger. So if you have a P particle coming closer to the H particle in that field, which is the line represented by the line, okay, so that H particle is going to pull this particle, and this guy weight, okay, weighted. So weight means like it resists that particle. The P particle resists, okay, the H particle. So we call that a drag, okay? So every time a particle resists, that means that particle has a mass, okay? Without the mass, it would not weight, or it would not resist, all right, another particle, okay? Try it. So suppose you pretend yourself as a particle and you go and approach to another, all right, person, and we're going to pretend another person is also a particle. So if you approach closely to another person, natural, our instinct is we move away. Okay, whatever that is. And if you actually make a force on it, also that particle is, okay, going to resist that force. Yeah. So anyway, so that's what happened in the experiment. Okay, so when you think about the photons, even though we say photons are particle, light particles, they don't have mass, by the way. Why? Because if you throw the photons, I'm going to write a P and little h, okay? When you throw the photon in the same Higgs field with the Higgs particle, the lines are, let's say, Higgs field filled with Higgs particle. So when H approaches to pH, it's not going to resist that. So therefore, we call the photons massless. Yeah, and this entire experiment, of course, is already been a theory. Yeah, and that is very important in modern particle physics. Yeah, and they have already validated that experiment. Higgs experiment, when they discovered Higgs boson. Yeah, 2012-ish. Okay, you can Google it. You can write his name Higgs and another particle named BO. Okay, SON boson. So Higgs boson was discovered in 2012, and this Higgs field, Higgs experiment, been completely validated. Okay, they have accepted it way before 2012, but the Higgs boson actually made it, made it a stronger validation for his theory. Yeah. So this is just trying to tell you why we use calculus in dynamics. Yeah, the role of calculus in dynamics is very huge. Yeah, because we focus on again, every time you think about calculus, you're thinking about the rate. The time rate of change. Everything is over time. Yeah, that's very important. Every time you think about time, you think about this little point to point interval line. Yeah. So anyway, so when you think about the velocity, that's the time rate of change of position, okay, or rate of change of position without the time, that's fine too. Acceleration, okay, other people call it rate of change of velocity. In formal writing is time rate of change of velocity. There's time, don't forget it, that line. Yeah, and then time rate of change of velocity is your acceleration, position is your velocity. Okay, so time rate of change of position your velocity. Time rate of change of velocity is your acceleration. Telling you again and again, time rates of change. We're dealing with calculus, yeah, right away. So every time you think about this little d, yeah, and then your variable, of course, this d, little d, is defining that change, okay, change. Okay, of course, we also use another symbol, like something like that. See that dot notation, yeah, right up there. So if you have a little dot with a little v, that's just showing you the change in velocity, yeah, over the little change in time, which is your acceleration, yeah. So that's just defining the time rate of change of velocity. So every time you see this, is that, yeah. And time rate of change of velocity, yes, this guy, velocity, and velocity is the time rate of change of position, yes. So velocity is the time rate of change of position. So v equal to x, and there's a little dot above x, and you're gonna put this, yeah, this into, plug it into there, yeah. So v is x dot, and v already has a dot above v for time rate of change of velocity, which is acceleration. So you're going to have two dots over x. So if you see two dots over the position symbol, you know that is acceleration. One dot over velocity symbol, you know that is the acceleration. One dot over position, okay, symbol, which is x, we know that that is your velocity, okay. So you should be able to recognize, yeah, see that little dot over x is v. We're gonna put the vs dot x dot in there. V already has a dot showing you the time rate of change of velocity for acceleration. So you want to write double dot x is your acceleration. Single dot v is your acceleration. Single dot x is your velocity. Okay? Alright. Of course, in the lecture, I will explain, okay, a little bit into it, but of course, for your course, we're excluding calculus, complex calculations, okay? So I should say complex calculations, yeah, using calculus. I am not going to ask you, yeah, so you don't have to worry about, don't feel bad because that's not included in our course, yeah. This is only purely conceptual, but you need to listen, okay, how things work in calculus and dynamics, so you at least get the concept of it, yeah. Of course, I will not ask you solve this problem with complex integration, but you need to recognize how we solve it, yeah. Yes. And so anyway, in calculus, yeah, especially in dynamics, we use derivatives and integrals, yeah. We use differentiation and integration, okay. So when we think about that, we're studying the relationships, yeah, between derivatives and integrals in the context of that calculus and dynamics. So we already study the relationship of position to velocity and then to acceleration, yeah, and we call that kind of progression or forward direction, yeah. So because the variable progress in a forward direction, meaning velocity depends on the change of position, acceleration depends on the time rate change of velocity, okay. So that's a forward direction progression. So your equation, look at that, how, yeah, they're going, see, velocity depends on the position, dot tells you what we're doing, complex calculation, which is studying the small change of position over a small change of time. Yeah, people usually call a change of position over time and forget about this change of the timeline. Yeah, timeline also have a distinct point because we always measure from the first point to the end point. Yeah, without the point, you will never get or be able to get the measurement accurately. So don't forget there is a change of time involved in it. Yeah, a lot of the, I don't know why educators neglect this little d, which is very important actually. Yeah. So anyways, the next one is I already show you. Yeah, the rate change of velocity is the double rate change of position to, yeah, to the change of time. So I would just say like the change of position to the double change of time. Yeah, and in fact actually you should write it this way actually. Okay, so anyways, that's I have already written that in previous slides for you. Okay, so you have see double rate of change of position over change of time, and then change of time 2 times here. Yeah, so that's what's going on for this acceleration. Okay, progression going that way. Integrals, okay, for integrals is when you solve the problem where you have known variables move in a backwards direction. Yeah, so derivative going forward direction, and integration going that way, backwards. Acceleration to velocity, and the velocity back to position. Yeah, in this analysis we're thinking in backward direction, because your variables is going to move from acceleration, velocity back to position. Yeah, so the equation, we're going to use a different integration symbol right there, like that. Okay, so now we go backwards, so we break this thing. Yeah, so bring this dt, yes, to that side, so we get v dt, and we have on this side you have d, all right, axis on this side. Since you bring this backwards, yeah, we put another calculation sign, and we still going backwards direction, trying to find the velocity from acceleration. Yes, and we calculate it this way, and we're going to use integration like that. Okay, so that's a forward, and then that's a backwards calculation. Yeah, just a little symbol to showing that, hey, we're calculating backwards, we're calculating forward. We do the same thing. Yeah, we're going to move this to that side. When you do it, we take integration, and then of course acceleration, change of time, equal to integration, and then change of velocity. See how easy, yes, that is. It's just like the way that they, the symbols, of course, the use of the symbols is probably making you feel difficult. You have to have courage to be able to get new things. Okay, I mean knowledge, of course. So this interplay between your derivatives and integrals is very, very important and fundamental in solving all the motion equations, in dynamics. Yeah. So again, to make it so simple for you, I spent a lot of time thinking on how to give it to you. So that's a forward, backwards. Okay, backwards, I should say going that way. Okay, but just writing it this way anyway. Going backwards, take integration. Going forward, do derivatives. Okay, differentiation. When we say differentiation, we're just talking about the mathematical operation. Yeah, so the name of operation is we're doing differentiation, and the results that you got are called derivatives. Yeah, integrals, results, integration, operation. Yeah, mathematical operation, meaning like you're doing some sort of a calculation. Yeah. Okay. So the department chair told me to teach the dynamics, conceptual, and to get rid of calculation, to get rid of simply put calculus. I was like, how do I teach dynamics without calculus? Yeah. So anyway, I tried. Okay, but anyway, you still need to listen. Okay, of how calculations is performed. So again, without the calculus, right, calculation is very difficult for us to be able to solve the problems in motions, which we call it the dynamics, motion of the objects. So understanding the derivatives and integrals, they're very, very important to because of the functions that we're dealing with in dynamics, as a function of time, you always hear it. So when you have to deal with the continuous functions, in the context of calculus and dynamics, and these guys are very important. So derivatives is going to help you to analyze how variables change with respect to another. You always hear like velocity, change of the position with respect to your time, acceleration, the change of the velocity with respect to the time. So there's a we're looking at, we're analyzing, we're studying, we're paying attention to how the variable change with respect to another variable. Integral, the same thing. We use it to get to measure or not measure, I should say calculate. Calculate the quantities like the total displacement for velocity or total velocity from acceleration. Displacement is just another distance, over a given another function, which is time, over a time interval. Time period and interval is just an interchangeable word, the same word, just an interval from one point to another. So integral again used to calculate the quantities. Okay, and we're always looking at one function over another. So again, all of this that we're doing is to describe the motion, describe the forces, describe the energy that comes with them, between these objects, a relationship, Okay, so every time we have to deal with the dynamics problem, of course, in this course, I am not going to ask you to calculate complex problem at all. So don't worry. You don't have to worry about it. But you do need to know how we do the things, okay? Because it's a vital part of dynamics. Because I don't want you to understand in a very wrong way. So it's my duty to teach you real dynamics, okay, how it works. So it's very important to understand the nature as the nature that we are in. Okay, all right. So solving dynamics problem, we have to use a method or approach, and that method we call a systematic approach, because you have to do it. You cannot solve a dynamic problem whatever way. Okay, you definitely need to solve one step after another, meaning do it systematically. That's because the motion is complex. Okay, because a lot of the things are not just moving in a straight line. They move whatever way they've been affected by the environmental forces. Environmental force again is not a single force. So many of them. You're being subjected to many forces at the same time, every second of your time. Okay, so when we handle the dynamics problem, we need a smooth progression, meaning like we want to solve it step by step. Why? Because you can check your mistake if you go step by step. Okay, I got wrong right here, let's go back, one step down. and we're going to fix it. So if you go step by step, you can minimize the simple mistakes. Yeah. And by doing that, we don't go into a huge mistake, so that keep our calculation accuracy intact. Yeah. um, Again, in science, we don't do things chaotically, we don't do things erratically, we don't do things whatever. Yeah, we do things by thinking. Okay. If you're not sure, don't do it. Make sure that you got everything in your power to move on to the next step. And that best practice, you got to start from simple calculation. Yeah, the more you do systematic approach, the better your accuracy is. Okay, in solving any kind of problem. It doesn't matter dynamic, yeah, problems or whatever problem in your life. If you do step by step, you're gonna have fewer mistakes or no mistakes. Yeah. So anyways, clarity, yeah, is just a structured method. um, Clarity is a structured method that's gonna make your work easier. Yeah, in science world, we make things easy. Like I'm making this complex course very easy for you, so you understand in a shorter amount of time. Yeah, so a structured method is gonna make your work easier for others to understand. Yeah, so it means, in other words, it's gonna help others interpret your work in a shorter time. Yeah, steps. So that's another one in systematic approach. We take in steps. I already explained that to you. So you're gonna follow the steps. Yeah. Of course, we have already organize the knowledge or the method, okay, in reference material or book how to do it. So you don't really need to struggle to learn how to solve a dynamic problem. All you have to do is to study how everybody else has solved for you and learn from it. Yeah. So follow the steps outlined in the reference material or book for all solved example. So we learn by reading, listening, imitating, yeah. Other people's examples are a great way to show you so you can imitate, yeah, how to solve step by step in a in in a systematic approach. Okay, so and that's going to ensure, so why we do is because to ensure the consistency, to to ensure the consistency, we use a proper method, yeah, in dynamic problem solving. Yeah, so make sure you use a structure approach. That is going to save your time. It's going to reduce the errors, possible errors. Yeah, especially when we attempt to solve complex dynamic problems. Dynamics problems are very, very complex. It takes a long time to solve complex problem is because motion, okay, motion is a complex thing, is a huge thing. Yeah. Alright, so this is just a section cover, and we're gonna go into universal gravitation. Yeah. So when we come to the universal gravitation, we're gonna go into the gravitational forces, and of course, what they do in dynamics. Yeah. So universal gravitation, you really need to know. Yeah, since we are here, that's our moon right there. So the gravitational force is a attractive force. Yeah, it attracts me. In simple word, it pulls. Yeah. Um, of course, that force exists between the bodies. In this example, we have two bodies. One is your Earth, and the other one is your Moon. Yeah, they attract. Okay, so gravitational force of attraction always exists between all bodies. Even though we show here in this example only two, you have so many bodies, in the space, so they all attract to each other, and this force depends on the masses of the body. Okay, when you look at this equation, see the mass is not only one. Okay, there are two in there. See that? Yeah. So this formula is showing you the gravitational, force. The gravitational force, and you have multiple bodies, masses of the bodies. Here, of course, we have only two here, A and B. Then we have distance, between that two, okay, bodies. So if you look at it, the distance is, let's say, okay, from here, the center. Let's just start from here, center to center, and that is your distance, which is this guy right there, and of course this is your mass, one, which is A here in this case, the mass A, that's got to be sub, and then of course the mass on B, my writing is very bad. So anyway, so this is MB and MA, which is this guy here, and then of course you have your G, that's your constant. That is a gravitational constant, which is always 6.67 times 10 to the power negative 11 Newton meter square per kilogram square. Okay, so that's your gravitational constant that we use to balance, gravitational force, because this is not very accurate, so we gotta put a adjusting constant of, to make this side equal to that side. Okay, without this, it's not going to be very accurate. You can't use the equal sign, and this is good enough if you use a constant of that value, when you measure the attractive force in between the two bodies. So this is your formula for your gravitational force. There are all the variables: gravitational constant, two masses here, and the distance between that two bodies. So that equation is just telling you the force increases, with mass, because it's directly proportional. If you get rid of this, you're gonna have a proportional, directly proportional symbol. So F is directly. So F is, I'm changing my color with this pen. So F is, anyway, the force is directly proportional to mass A, mass B. See, we're getting rid of this constant, and your force is indirectly, okay, proportional to the distance in between them. Yes? Okay, meaning if this distance is longer, your force, gravitational force, decreases. If this distance is smaller, meaning if the bodies are closer, your gravitational force increases, is bigger. Then we're gonna come into universal gravitation, and that's another review of your physics, your Newton's third law of motion. This is the third law of motion. Is your universal gravitation. So when you think about each body, exerts an equal and equal but opposite gravitational force on the other body, you're gonna have like that force exerted by A on B is actually equal in magnitude, but opposite in direction to the force exerted by B on A. Okay, so now you have two bodies. This is going to exert a force on that, and that is going to exert a force on this. Okay, because since you're exerting the force from here to there, the direction is going that way. Since you're exerting the force from here to here, the direction is going this way. So you have opposite direction. Okay? But you have the equal magnitude, yeah, of that force. So this is a direct consequence, yeah, of that formula we just saw, you know, which is if you remember, your gravitational force is equal to your constant g, yeah, and then divided by, here is mass A and B divided by the distance in between them. Okay, I usually use a mass 1 and 2, but right now in this example they're doing it B and A and like that. So but it's the same thing anyway, so your D, and then of course we need, don't forget the square here. Yeah, so two forces, both forces, they are equal in magnitude. Why? Because they depend on the same values of mass. Mass doesn't change, okay, and distance, okay, and the gravitational constant. That doesn't change. This doesn't change, and the mass A doesn't change. The mass B doesn't change. Therefore, the force is the same, but in different direction. Okay, you can say like just because of the mass of B is bigger than the force of this is bigger. No, not like that. We're not just taking a single mass, we're taking the multiplication of both masses. All right, so these little things that you gotta be very careful. Okay, all right. So we're looking at the value of the multiplication of mass A and B instead of just mass A or mass B. So therefore the force, yeah, gravitational force of A on B, gravitational force of B on A is the same in magnitude, but the direction, yeah, of that applied force is different, going this way and going that way. So therefore the forces of A on B and the forces of B on A is equal in magnitude but opposite in direction. Yeah? So the Newton third law, if you need to review, right? So he found out about how important the gravitational interactions. Why? Because the gravitational interaction between two bodies are mutual. Yeah, we're not considering each mass separately. We're considering the interaction of the masses together. I mean, multiplication of this and that together. Yeah, value. This is a single value because we're considering the value of the operation of two masses. So that interactions are mutual. And then of course they align with the principle of your action and then reaction. Okay, so action and reaction force, same magnitude but opposite directions. Yeah, so that's your Newton's third law of motion. All right, so now we understand how important this value, okay, of this operation, which is multiplication, is in gravitational force or attraction. Yeah, and we're gonna do this a small problem to understand that. Yeah, so we have two pairs of particles, A and B, and then we have C and D. That's your first pair. Second pair, see, we use the word pair. Yeah, so therefore we know that there are two masses, yeah, mass A and mass B, mass C and mass D for this pair. Second, this is the first pair. Yeah, and so we are to think about which particles experience the greatest gravitational attraction. So there is attraction, gravitational force in between them. The gravitational force is the same in magnitude and different, yeah, in opposite direction. So this is going to exert on here and that is going to exert on here, and we are looking at the masses in a pair, meaning like we're going to take the value of this operation. Okay, so we're going to decide which pair, which particle experience the greatest. So you have four choices. Yeah, particle A has only 1 kilogram. Um, our problem is dealing with gravitational attraction. So you can eliminate A and C right away, okay? Because it only consider a single particle. Because in gravitational attraction, we consider two, okay? Two objects. So in this case, two, got to be two particles. So therefore, B and C is what you're gonna think right away. Okay, see how easy process of elimination is. So now we have A and B and C and D. When you look at it very carefully, you know that that's the same. So now I don't even care about this. Yeah, and also G is constant, so that's gonna be the same. So my concentration goes straight to the mass. Yeah, and again, don't forget about the R. Yeah, pair. Yeah, that's the first pair, second pair. So we got to think about the operation. Mathematical operation is multiplication of two masses. So I go and look at it. Yeah, since they are operable, they have values. Yeah, so we have 1 and 5. Since we're using the same unit, we don't even have to do a conversion. So units are out again. See how I eliminate everything? Yeah. So I only have to deal with 1 and 5 and 2 and 3. Yes. So this is how we calculate. Okay. Of course, I'm gonna plug that in. Yeah, into there. So you can go like 1, 5. Yeah, and distance is 2. So divided by 2. When you calculate it, you're gonna get about constant G. Yeah. So 1, 5, 5, 4. Yeah. So I'm just plugging in 1 here and 5 right there. So that's 5 times 1 is 5 divided by distance is 2. So therefore it's going to be 4 down there. Yeah. So that's G is equal to not G. I mean the F is equal to I should write it. F is equal to G times. Okay. Let me get my. Because everything is messed up here on this side. Okay, I am going to erase this, okay, for you, and let me just write it down here. Where's my line? Oh my gosh. Okay, so F, okay, is equal to, the very first one is a big G, because G doesn't change, constant. Yeah, so your F is G equal to 5 by 4. And we're going to do the second F. Yeah, so that's your first pair. And the second one is going to be, when you plug it in 2, 3 is going to be 6. Yeah, and then down here is 4. So the second F is 6 by 4. Yeah, and the first F is 5 by 4. So 5 divided by 4 is 1.25, and then 6 divided by 4 is 1.5. Okay, 1.5. So therefore, we know that particle C and D, okay, is gonna give you the greatest gravitational attraction. See that? You can go straight, okay, without writing it like that too, because since distance is the same, yeah, you can cancel this right away. So you're down to 5 compared with 6. Yes, so therefore you know that this is going to give you the bigger gravitational attraction. Okay. All right, the next problem you have, again, to pass the particles 1 and 2, 1 kilogram, 2 kilogram mass with 1 meter apart, 2 kilogram, 3 kilogram masses with 2 meter apart. Yeah, and we have to compare the gravitational attraction between them. So we get rid of this right away because gravitational attraction, we are thinking about two particles, not just one. We have particle A and B, C and D. This time, okay, we have a distance. Look at this distance. They're different, yeah? So gravitational attraction is bigger when the distance is closer, yeah? But we don't have the same mass. We have different masses in different pairs right here. First pair, and then this is your second pair. So we're gonna do our plug-in method, yeah? So the first one, you're gonna plug in 1, 2, and then 1, yeah? So you will get, if you quickly do the math, 2 times 1 is 2, right? Divided by 1 is going to give you G, okay? You're going to get 2 here, yeah? The second one, you're going to plug in 2, and then you're going to plug in 3, okay? So that is going to give you 6, okay? So I'm going to write a G here, yeah? And then I'm going to write a 6 here, and 2 times, okay? 2 is going to give you 4 again, as in the previous example. Yeah, so this we already knew. Yeah, if you calculate it, you will be getting like 1.5. Yeah, so 6 divided by 4 is about 1.5. Yes, so 1.5 and 2, when you compare, you know that 2, see, that is greater than here. So therefore, your particle A and B pair is going to create greater gravitational attraction. All right, shorter distance, greater F. Okay, we're done with this introduction, chapter 1. Yeah, we have many sub sections, so the lecture is pretty long, about like 3 hours, but you don't have to listen straight. Just go pause, listen about 30 minutes and come back. You can do that because you have like the entire week to pre-listen to the lecture, so we can be able to do the problems, okay? Your exercise in class, right? All right, I'm gonna let you go now, and we're gonna go into chapter 2, in next section.